Hello, hello, hello. Today is September 7, 2021. I posted today a problem that has kept me awake for years. And this video will contain the correct solution. But I want to tell you some of the background about my sleepless nights. I have lectured at MIT electricity and magnetism. I was 43 years on the MIT faculty. I never got a clear-cut answer. What happens when you move a magnet through a closed loop that is completely made of superconducting material? Some students may have asked me about that, and I may have told them that I didn't know. I don't remember. It has kept me awake for years. And then I just blocked my mind and said, well, you can't know everything. But in 2019, 10 years after I retired from MIT, I decided to write that problem that I had to about 17 prominent physicists in the world. Included MIT, Harvard, Princeton, Northwestern, Germany, the Netherlands. This is the problem, which I wrote. I have a coil exclusively made of superconducting wire. The ends of the coil are connected also with superconducting wire. Thus the circuit is a superconducting closed loop. I move a magnet in and out of the coil. There is a phi dt, magnetic flux change, which changes in time, Faraday's law. I state here, Faraday's law does hold. Will there flow an electric current in the closed loop? And if so, how does it change in time? But the puzzling thing is, there cannot be an E field in the wires and not in the coil. So I got stuck. Can you tell me how all this fits together? 5 answered they feel embarrassed, very prominent physicists, but they don't know. And they asked me, if you ever find out, let us know. There were 5 interesting answers, but they were not really solutions, because they only covered one of the issues with at stake. For instance, the role of Faraday's law. But not the overall self-consistent solution that made you all of a sudden say, oh my God, yes, of course, that's the way it works. But I want to thank those 5 people. At least they answered me. The first one was Professor Rossio from Northwestern. George Clark, my close friend from MIT. Ray Weiss, also a friend of mine from MIT. Also a Nobel laureate, by the way. Professor Ketterle, Wolfgang Ketterle, also from MIT. Also a friend with whom I often have dinner and met his wife. Also a Nobel laureate. Professor Scott Hughes, who really understands this material very well. but he also had problems. So, oh, there was one professor, by the way, at MIT, I will not mention his name, who said there's really no problem, because it's true that a constant E field cannot exist in superconductors, but a changing E field can exist in a superconductor, and so that solves the problem. Well, of course, that was dead wrong. Almost 2 years went by, and my wife sent me a note that Professor Avi Loeb of Harvard was going to give a talk online at the University of Connecticut. We live very close to the University of Connecticut, which is called UConn. I have known Avi for some time, long ago when I did most of my research in X-ray bursts. I do not remember anymore what our discussions were about, but they were definitely about astronomy. So, my wife and I listened to his talk. He is a theorist in physics and in astronomy. He has had a lot of publicity lately with his new book, Extraterrestrial, The First Signs of Intelligent Life Beyond Earth. He's been on NBC News, on CNN, and in the newspapers. And his talk was about that too. I enjoyed the talk. And I wrote him the next day, I think the talk was on September 3. And I wrote him the next day and said, Avi, this was really a great talk. And then somehow, I don't know why, I decided, what the heck? I've been waiting now 2 years, why don't I send this problem also to him? And I did. As you see it here. I also add a line and say, if you're busy and don't have time, I understand that. He answered me within 24 hours. On September 4, Dear Walter, no current inside the superconductor, where E equals B equals 0, only surface currents. At any time, the surface currents are such that they produce an opposite magnetic field internally and cancel the external field inside the wire. Given that the external magnetic field varies in time, because I move the magnet right in and out, these currents vary in time, so as to cancel the external field at any time. Therefore, you end up with a surface current that satisfies Faraday's law outside the wire by generating an electric field that satisfies Maxwell's equations, but there is no current in the interior of the wire. When I read it, and I'm very honest to you, I got tears in my eyes. I knew this is what I had been waiting for 2 years. And that night, I couldn't even sleep. I told you that I wrote this problem to about 17 people. 5 told me they couldn't do it. 5 sent me some kind of an answer. And from 7 I never heard. And I would imagine that Maybe some of them had no time, but I'll bet you most of them couldn't do the problem either. And here were the solutions. I had some more exchanges, of course, with Avi about that later. And he and I agree that really at the heart of the solution is what I made the red statement. Therefore, you end up with a surface current that satisfies Faraday's law outside the wire, it's at the surface of the wire, by generating an electric field that satisfies Maxwell's equations. That is the heart of the whole issue. Once you have that, you're on your way. Therefore, we agreed that if I make this a problem on my YouTube channel, that anyone who answers me, if the heart is missing, and this is the heart, then the solution is dead and is wrong. It's now September 7. I made the statement that most physics professors cannot do this problem. That, of course, included myself. The only correct solution of the 17 requests came from Professor Leu. So my statement that most physics professors cannot do this problem was a correct statement. I was even a little bit naughty. I wanted to tease my Indian friends who are so proud of Professor Verma. He's a great professor, there's no question about that. His lectures are famous and his book is famous. So I even dared to add, probably Professor Verma cannot do it either. Oh my God. I wish I hadn't said that. But I did. And I really believe that he probably cannot do that. If he is smart, he should not put the answer on my YouTube channel, because if he doesn't write on my YouTube channel, no one will ever know whether he knew how to do it. So we'll leave it for this. 2 weeks from now, I will finish the solutions because I want to add the names of the people, if there are any, who had correct solutions. So for now, September 7, over and out, and see you again, perhaps in a week, maybe sometime around September 14. Hello, hello, hello. Today is September 14, 2021. I will now address the issue about solutions that people have sent me. There have been 31,000 views with 640 responses, solutions. Let's first take a look again at the correct solution by Professor Avi Loeb. No current inside the superconductor, where E equals B equals 0. Only surface currents. At any time, the surface currents are such that they produce an opposite magnetic field internally and cancel the external field inside the wire. Given that the external magnetic field varies in time, these currents vary in time so as to cancel the external field at any time. By the way, that's what we also call the Meissner effect. Therefore, you end up with a surface current that satisfies Faraday's law outside the wire by generating an electric field that satisfied Maxwell's equations. But there is no current in the interior of the wire. So he addresses the issues that I placed in the problem to you. Is there a current in the superconductor? And if so, isn't that strange, because electric field is zero? And if the answer is no, there is no current, then you wonder, what is the role of Faraday's law? Is Faraday's law perhaps violated? Here you see the answer. Faraday's law is not violated. The beauty is that the current caused by Faraday's law is only on the surface of the superconductors. Now comes the news that doesn't surprise me. No one sent me a correct solution. At the heart of the correct solution is the part that I printed here in red. Therefore, you end up with a surface current that satisfied Faraday's law outside the wire by generating an electric field that satisfies Maxwell's equations. Of the 640 answers, none were correct. Many of you said things that were certainly wrong, sometimes including things that were right. Some were weird. Some people say you can never move the magnet into the coil because the coil will repel the magnet. Well, sorry, I call that really absurd. The best solution, even though not exactly correct, is the one by George Hnatyk. He recognizes what is at the heart of the solutions. Therefore, you end up with a surface current that satisfied Faraday's law outside the wire. That is at the heart of the solutions. If this is missing, your solution has no heart. You have created a dead animal. The solution is then wrong. George certainly recognizes that. Let's take a look at what George wrote. So here is George Hnatyk, September 8. No B field in the wire. For a time-varying current to flow as the magnet is moved, there must be a tangential E field along the conducting surface which produces a surface current density, even though the E field cannot penetrate the perfectly conducting wire. That's crucial. Faraday's law demands an induced electric field be generated on the surface of the wire, so a surface current will flow on the wire surface. This, of course, implies, even though he doesn't put it in words, but it's obvious, that if Faraday's law can only produce a current on the surface, then clearly there will never be a current in the superconductors. So he didn't mention that, but I in the conductors is zero. He happens to know that the B field in the wire has to be zero because of Meissner's effect. he fails to say that it is the current, the surface current on the superconductors that are responsible for the zero field inside. If you add the magnetic field that is produced by the surface current to the magnetic field that is produced by the moving magnet, the net result is zero. He doesn't mention that connection. Therefore, I cannot call him that it is a absolutely correct solution. But I would say 95% correct. And I would say, therefore, he really is the only one who nailed it. Well, actually, it's only Avi Loeb who nailed it. George Anatiuk almost nailed it. There is no correct solution. Am I surprised by that? No. Didn't I mention in my problem that I'll be happy even if there is one correct solution? Let me call this one correct, even though it's not completely correct. Read again the solution by Professor Avi Loeb. I cannot add anything to that. When I read it, it was a total eye-opener for me. I realized when I read the statement that Faraday's law creates an E field outside the wire, causing a current, I immediately knew that that's the point that I have always overlooked. So for me, this was an eye-opener. Believe it was that. I cannot add much more. I have said several times, most professors cannot do this problem. 17, whom I wrote, world-famous physicists, could not do the problem. 5 even admitted it and said, oh, we can't do it. 2 of them, who gave it a shot, but was not a completely correct solution, are Nobel laureates. So no one, no physics professor in the world should feel bad if he or she also cannot do the problem. I will have to leave it with that as far as the solutions is concerned of my viewers. I mentioned that most professors cannot solve this problem. I sent the problem to 17 people. None of them could solve it. Some of them actually said they're sorry, but they have no clue. None of them sent me correct solution. 7 of them never answered, which I believe probably because they couldn't do it either. Since I said most professors cannot solve this problem, I said, which I regret after the fact, probably Professor Verma cannot solve the problem either. I have an enormous respect for Professor Verma. His lectures are famous, and so is his book. But solving this problem is a different issue. Avi Loeb was the only person of 18 well-known professors who snapped it and had the solution in less than 24 hours. I was hoping that Professor Verma would not make an attempt to explain it, Because if he never made the attempt, no one would ever know whether he can do it or not. Well, he put a video on his channel, and of course, my viewers sent me the website. And so I watched the video a few times. Hold on to your chair. It's blatantly wrong. Yes, it is. He believes that because of Faraday's law, there will be a current into the superconductor. And then he uses somehow the B field that is caused by that current to eliminate also the B field from the magnet, so that the net B field is zero. There cannot be any current in the superconductor. In principle, there can be a current in a superconductor, and of course still the electric field everywhere is zero. In principle, that can be done. You take a battery which has an internal resistance R, voltage V, and you short it out with a superconductor, and if you wait long enough, a current will flow I, which is V over R. And that current has to go through the superconductor. The E field that is produced is in that resistor R. That's why it works. But in our case, the entire loop is superconducting. So there is no way that ever any current can flow in the superconductor. Watch Professor Verma's video again. It's blatantly clear. He puts it there. And then he jumped through a few more loops to somehow, I think he even introduces Lenz's law to somehow argue that that current in the superconductor produces a B field that cancels the B field of the magnet. It's wrong physics. The beauty is that Faraday's law creates electric field, an EMF, just outside the superconductor. At the surface of the superconductor, there will be a current. And that is possible, because at the surface of the superconductor, the resistance is not zero. Isn't that beautiful? How nature works? And it is that current at the surface of the superconductor that causes a magnetic field, straightforward, it has nothing to do with Lenz's law, a straightforward magnetic field that added to the magnetic field due to the magnet adds up to zero, and that's what's called the Meissner effect. Well, I may lose all my 1 million Indian subscribers. Professor Loeb also watched the video by Professor Verma, and he came to the same conclusion. He said, yeah, of course, it's blatantly wrong. He knows how important India is for me and how much this may be upsetting many Indian people. So he said to me, you know, Walter, what you should do, just say that Verma's solution is incomplete. I said, but Avi, many other wrong solutions are incomplete. Should I mention all wrong solutions that are incomplete? And he started laughing. And he said, Walter, you're right. Call a spade of spade. It's wrong. End of story. Now, I want to stress once more. Should Professor Verma feel bad about this? No, not at all. I couldn't do it either. He gave it a shot, as several other of the people whom I asked, world-famous scientists. Some of them also gave it a shot. Everyone failed, except Avi Loeb. So, is it so bad to admit that it's wrong? No. He's a great man, Verma. He will always be that for me. And it is irrelevant, truly irrelevant for me, that his solution to this problem is wrong. And it should also be irrelevant to you. So this is the end then of this very difficult problem. And I hope there will not be unpleasant ripples in the future. I'm not going to argue about this any further. This is my last word on it. We're going to move on to another problem, 120. Have a nice time. Take care. And we'll be friends. And I'll be friends with Professor Verma. And I hope he wants me to be his friend. I would like to add that in April 2014, I gave a lecture at the Indian Institute of Technology in Kanpur. And I had hoped that Professor Verma would be there. But he wasn't. He was retired and probably had more important things to do. Great school. I was 6 weeks in India and gave 8 lectures at different institutions and universities. All great schools. All 8. All 8 great.